Welcome back, students. Welcome to lecture 2 of the lecture series in FIR filters. In the previous lecture, we have studied the introduction part of FIR filters, where we have discussed some of the advantages as well as the disadvantages of FIR filters, which makes us to choose between IIR and FIR filters. And we have also discussed about certain points such as the LDI systems always acting as a frequency selective filter, and we have discussed about the ideal frequency response of the basic filters such as low pass, high pass, and band stop filters. And we have said that the ideal filters are generally non-causal and hence physically unrealizable for real-time signal processing applications. And we have also seen that in practice it is not necessary to insist that the magnitude will be constant in the entire pass band, and a small amount of ripple in the pass band is usually tolerable. Similarly, we have discussed about some key characteristics of FIR filters. We have studied about this FIR filters having linear phase, and we were able to gather 2 points whenever we were able to gather 2 points, and saying that whenever from the condition that what we have derived yesterday, we have seen that for whenever h of n is equal to h of n minus 1 minus n, for the value of alpha is equal to n minus 1 by 2, then the h of n has a special kind of symmetry and and similarly when it also exhibits linear phase whenever with anti-symmetric impulse responses, and it has once again the center of symmetry at n minus 1 by 2, and their impulse response are anti-symmetric also around the center of the sequence, as opposed to the true linear phase sequence that are symmetric in the previous cases. So we have also seen these examples of symmetric impulse responses and anti-symmetric impulse responses, and this is what we have actually covered in the last lecture. In this lecture, we will study about the frequency response of linear phase FIR filters. The frequency response is nothing but the Fourier transform of the impulse response. Depending upon the value of n, that is the number of points in the impulse response, the number of points in the impulse sequence, whether they are odd numbered or even numbered, and based upon the type of the symmetry of the filter's impulse response, that is, it is either symmetric or anti-symmetric, there are 4 possible types of linear phase FIR filters, and these are the following, that what we have shown under the heading of case 1, 2, 3, 4. They are the 4 cases of impulse responses for linear phase FIR filters. In the case 1, we can just say that they are symmetric impulse responses, and n is odd with the value of its samples odd numbered with the center of symmetry at n minus 1 by 2. Similarly, case 2, symmetric impulse responses, and n is even with center of symmetry lying at n minus 1 by 2. So we will categorize the impulse responses into these 4 cases, and we'll try to find out the frequency response in each case, and we will note down the magnitude response of those filters for our future use. Let us deal with this case 1 first, where I consider a symmetric impulse response with the values of its samples odd numbered. Let us consider a impulse response which is symmetric, and the value of n is odd with the center of symmetry at n minus 1 by 2, and I am trying to find out the frequency response of linear phase FIR filter. The frequency response is given by this equation, where h of e power j omega represents the Fourier transform of the impulse response of the system, where small h of n represents the impulse response of FIR filter, and since h of e power j omega is a complex function, I would also like to express it in the form of magnitude and phase functions. I would like to summarize after the derivation the frequency response of these kind of impulse response is given by h of n minus 1 by 2 plus sigma n is equal to 1 to n minus 1 by 2 2h of n minus 1 by 2 minus n into cos omega n multiplied with an exponential e power minus j omega n minus 1 by 2. As I said, since the Fourier transform is complex in nature, it is represented both with respect to the magnitude and phase spectrums, and the magnitude spectrum is represented with a of omega, and the phase is represented with respect to theta of omega. The amplitude function derived from this h of e power j omega is represented as h of n minus 1 by 2 plus sigma n is equal to 1 to n minus 1 by 2 2h of n minus 1 by 2 minus n into cos omega n. Since the magnitude function of e power minus j omega n minus 1 by 2 will be equal to 1 under root of cos square omega of n minus 1 by 2 plus sin square omega of n minus 1 by 2, this leads to 1. That is the reason we are able to see that the magnitude response function does not have any value of this e power minus j omega. Similarly, the phase function is related to this omega of n minus 1 by 2 with a negative sign, therefore it is represented as phase function is equal to minus of omega into n minus 1 by 2, where this n minus 1 by 2 is represented with a constant like alpha. It's worthy to note a point related to this magnitude response of this kind of a filter, and this can be remembered so that it can be used in various problems that we encounter in the coming lectures. However, so I would like you to prove this, how we are able to actually derive this h of e power j omega in this case, for this case 1, and for the rest of the cases the readers are encouraged to solve and check whether the results are the same. So I have done the proof for you on the coming slides. Let us go through this proof. As I have said, I have considered a h of n which is symmetric and has its values from 0 to n minus 1. Since it is symmetric with respect to n minus 1 by 2, it has its values evenly spread before n minus 1 by 2, that is from 0 to n minus 1 by 2, and similarly it is evenly spread from n minus 1 by 2 to n minus 1. So based upon since we are trying to find out the frequency response of h of n, so we need to find out the Fourier transform of h of n. The Fourier transform of since h of n is discrete in nature, I represent the discrete time Fourier transform of h of n as h of e power j omega is equal to sigma n is equal to minus infinity to plus infinity h of n into e power minus j omega n. Since this h of n has its values only from 0 to n minus 1, I change the limits from 0 to n minus 1. And this represents a Fourier transform equation of our h of n. As I have already said, this h of n is odd numbered sequence and it has a symmetric impulse response with the center of symmetry at n minus 1 by 2. H of e power j omega now can be expressed with respect to various values of h of n. Since it has symmetry, I write this as sigma n is equal to 0 to n minus 3 by 2 h of n into e power minus j omega n, and it has its center of symmetry at h of n minus 1 by 2. Therefore, writing that sample at h of n minus 1 by 2, h of n minus 1 by 2 into e power minus j omega n by 2 plus sigma n is equal to n plus 1 by 2 to n minus 1 h of n into e power minus j omega n. This particular impulse response is split based upon the symmetry of its based upon the symmetric nature of the response. As we have seen now in this case, as we have already said that with respect to the symmetry, generally h of n is equal to h of n minus 1 minus n. We have already able to see this in the previous lecture. For symmetric impulse responses, h of n minus 1 minus n is equal to h of n. Therefore, you can directly substitute it, or else you can also have a variable change here. Let us consider n is equal to, or else with some particular m, where let m is equal to n minus 1 minus n, and we change this n with m so that it can be represented as n minus 1 minus m. When we brought this kind of a change, there is a change with respect to the limits too, and therefore when n is equal to n plus 1 by 2, the limit is from n minus 3 by 2 now, and when n is equal to n minus 1, m is equal to 0. So, bringing out these changes with respect to this particular expression here, I find it as sigma m is equal to 0 to n minus 3 by 2 h of n into e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega n minus 1 by 2 plus sigma m is equal to 0 n minus 3 by 2 into h of n minus 1 minus m into e power minus j omega n minus 1 minus m. Once again substituting with m is equal to n, I find this as h of n minus 1 minus n and e power minus j omega n minus 1 minus n. I have rewritten the equation just by substituting m with n, and I have rewritten the above equation. As we know, for symmetric impulse responses, h of n minus 1 minus n is equal to h of n. I once again substitute h of n minus 1 minus n with h of n, and therefore this equation can be rewritten as h of n into e power minus j omega n, h of n minus 1 by 2 into e power minus j omega n minus 1 by 2, and this n minus 1 minus n is substituted with n. Therefore, h of n e power minus j omega n minus 1 minus n. And now grouping these similar expressions with respect to the similar limits from n is equal to 0 to n minus 3 by 2, we have h of n minus 1 by 2 plus, and also taking this e power minus j omega n and as a common term and multiplying with all those terms, I have this as sigma n is equal to 0 to n minus 3 by 2 h of n into e power minus j omega n e power j omega n minus 1 by 2. Since we have taken this term common, I multiply this with e power j omega n minus 1 by 2, and similarly here also I have multiplied with this n minus 1 by 2. And rearranging the terms, we have this as e power minus j omega n minus 1 by 2. And now I have written the same equations for your convenience once again. H of n minus 1 by 2 plus sigma n is equal to 0 to n minus 3 by 2 h of n, so on. And now expressing this particular equation in terms of this cos theta, because we know that the trigonometric ratio cos theta can be represented as in terms of exponentials as e power j theta plus e power minus j theta by 2. So since we doesn't have a factor of 2 here, multiplying it with 2, I have h of n minus 1 by 2 plus sigma n is equal to 0 to n minus 3 by 2 h of n into 2 cos of n minus 1 by 2 minus n into omega, multiplied with e power minus j omega n minus 1 by 2. This gives us a final expression in terms of cos omega n, and this is what our frequency response is, that what I have represented in the previous slides. H of n minus 1 by 2 plus sigma n is equal to 1 to n minus 1 by 2 h of n minus 1 by 2 minus n into cos omega n whole multiplied with e power minus j omega n minus 1 by 2. This represents the frequency response of our symmetric impulse response, that what we have considered, and this is what I have mentioned here in this particular slide. And readers are once again suggested to practice or to derive this frequency responses in each individual cases. I would also like to show you a typical sketch of this symmetric impulse responses for n odd values. In this case I have considered for n is equal to 9 and its corresponding amplitude function, that is the magnitude function of the frequency response in the figures. From these sketches it can be observed that the amplitude function is here it was a normalized. I have normalized with respect to pi, therefore the x-axis is represented with respect to the integer value. Generally this particular value represents pi. From these sketches it can be observed that the amplitude function is symmetric with respect to omega is equal to pi. With respect to omega is equal to pi, it has whenever we consider with this particular value, it is symmetric, and here as I have already said, this n is also considered to be an odd number which is equal to 9. When the impulse response is symmetric and n is odd, the frequency response is non-zero at 0 as well as pi, and so this frequency response can be used to design low pass, high pass, band pass and band stop filters. This is what I was talking about, a symmetric impulse response. Actually it has its center of symmetry at alpha is equal to n minus 1 by 2. In this case, since we have taken n is equal to 9, alpha is 4 here, and it is symmetric with respect to this n is equal to 4, small n is equal to 4. For this kind of a symmetric impulse response, when n is odd, we are able to see the amplitude response and able to derive the frequency response of it. And similarly, now I would also like to represent the frequency responses in all the other cases that what I have discussed earlier. For case 2, the frequency response of linear phase FIR filter, when impulse response is symmetric and n is even, it's not n is odd here, it is n is even with center of symmetry at n minus 1 by 2. Considering n is even, I make a pardon, here n is considered to be even. With the frequency response of linear phase FIR filter, when impulse response is symmetric and n is even with the center of symmetry at n minus 1 by 2, the frequency response equation, the frequency response is represented with respect to this expression, h of e power j omega is equal to sigma n is equal to 1 to n by 2 to h of n by 2 minus n cos of omega into n minus 1 by 2 e power minus j omega n minus 1 by 2. Readers are encouraged to once again derive the Fourier transform of such a impulse response where h of n is equal to minus h of n minus 1 minus n with n even values, in center of symmetry lying at n minus 1 by 2. In such case, now you can split this h of n only into two parts, from 0 to n by 2 minus 1 and from n by 2 to n minus 1. You can just split from 0 to n by 2 minus 1 and n is equal to n by 2 to n minus 1, and you can just check how this symmetric impulse response with the even number of samples shows the frequency responses. Okay. I suggest you to go through this, and the magnitude function in this case is generally represented with respect to magnitude of sigma n is equal to 1 to n by 2, 2h of n by 2 minus n cos of omega into n minus 1 by 2. The sketch of symmetric impulse responses for n even, in this case I have considered n is equal to 8 and its corresponding amplitude frequency response, that is the magnitude response, was also shown in the figure. As I said, it is symmetric once again, but here in this case now it is symmetric with respect to the center of symmetry at n minus 1 by 2, which is equal to 3.5. Since this particular center of symmetry is not considered in the is not included in the samples of the impulse response, we directly express it from 0 to n minus 1 by 2 plus n minus 1 by 2 to n minus 1. Okay, and this represents the symmetric impulse response with n even. And for such kind of impulse responses, generally the magnitude response will be something like this. From these sketches, it can be observed that once again that the amplitude function of h of e power j omega is anti-symmetric here. It is anti-symmetric with omega is equal to pi, where your impulse response is symmetric and n is even number. The frequency response is also non-zero at n is omega is equal to 0 and at omega is equal to pi. So this frequency response can be better used to design low pass and band pass filters, but cannot be used to design high pass and band stop filters. In the third case, once again with the frequency response of linear filter, where impulse response is now considered to be anti-symmetric and n is odd with its center of symmetry lying at n minus 1 by 2, I derive the frequency response something like this: sigma n is equal to 1 to n minus 1 by 2 2h of n minus 1 by 2 minus n sin omega n e power j pi by 2 minus omega n minus 1 by 2. And the magnitude response and the phase response of this frequency response was also given, and the magnitude function is mentioned here, sigma n is equal to 1 to n minus 1 by 2 2h of n minus 1 by 2 minus n sin omega n. This is the magnitude response whenever we consider the impulse response to be anti-symmetric and the number of samples are odd numbered with the center of symmetry lying at n minus 1 by 2. The typical sketches once again for this anti-symmetric impulse responses when n was considered to be 9 and its corresponding amplitude response is also shown in the figure, and we are able to see that once again it observes it can be observed that the amplitude function is once again anti-symmetric with omega is equal to pi, where its impulse response is also anti-symmetric for n is equal to odd number with its center of symmetry lying at n minus 1 by 2. Here the term e power j pi by 2 makes this frequency response imaginary, and hence this frequency response is only suitable for designing a special type of transformations or filters such as Hilbert transformers and some differentiators. you are encouraged to solve once again the frequency response of this kind of impulse response also, and where now the impulse response can be split in from n is equal to 0 to n minus 3 by 2, and similarly at the center of symmetry, and from n plus 1 by 2 to n minus 1, as what we have done in the case 1. You can once again split your impulse response into the same things and you can proceed further, but you'll be able to see that there is a term with respect to your exponential which is equal to e power j pi by 2, and this is an imaginary term actually, and this makes our frequency response imaginary. And case 4, whenever the frequency response of linear phase FIR filter when considered with its impulse response is anti-symmetric, and n is considered to be even with the center of symmetry at n minus 1 by 2. In such case, once again the frequency response is actually represented with this expression: sigma n is equal to 1 to n by 2 2 h of n by 2 minus n sine of omega into n minus 1 by 2 whole multiplied with an exponential e power j pi by 2 minus omega of n minus 1 by 2. And the magnitude function in this case was also given as sigma n is equal to 1 to n by 2 2 h of n by 2 minus n sine of omega into n minus 1 by 2, and the phase here is typically equal to beta minus alpha omega, represented with respect to this, where beta is equal to pi by 2 and alpha is n minus 1 by 2. This is case 4 actually. Here I have mentioned it as case 3, but it is equal to case 4. Anyways, we have now seen 4 different cases with impulse response having odd and even numbered samples, and also classified as symmetric and anti-symmetric impulse responses. Now the fourth case, I would like to show you the typical graphs involved with this fourth case, where your impulse response is anti-symmetric for even number of samples, and its corresponding amplitude response is also shown. And here from these sketches it can be observed that the amplitude function of h of e power j omega is symmetric with omega is equal to pi when the impulse response is anti-symmetric and n is even. And the term once again e power j pi by 2 makes this frequency response imaginary, hence this particular frequency response is also suitable only for designing Hilbert transformers and differentiators. And 2 special cases can also be derived from case 1 and case 3 by making the center of symmetry at n is equal to 0, having the sample spread both with respect to this negative numbers as well as the negative integers and the positive integers. We can also have 2 special cases derived from case 1 and case 3, and I would like to mention this, summarize all those typical magnitude responses for you. As I was talking about 2 special cases, these are the 2 special cases that I would like to talk about. The symmetric odd, the case 1, once again here considered to be this h of n minus 1 by 2 made to be this n minus 1 by 2 made to be 0, and therefore it was represented as h of 0 plus sigma n is equal to 1 to n minus 1 by 2 h of 0 minus n. Since h of minus n, since we observe this symmetry here, I represent it as h of n into cos omega n. H of minus n is equal to h of n in this case, therefore 2h of n cos omega n. This is a case which is derived from this symmetric, the case 1, where we have a symmetric impulse response with n is odd, but the center of symmetry now lying at alpha is equal to 0. In the previous case the center of symmetry was at n minus 1 by 2, but here now alpha is equal to 0. Similarly from case 3, once again you can make that center of symmetry equal to 0, and typically see that h of minus n is equal to minus h of n, and by substituting these kind of relations in this particular expression, we derive sigma n is equal to 1 to n minus 1 by 2 h of n sine omega n.
And this slide is going to be very important for us to remember the magnitude functions, so that they can be used in the frequency responses whenever it is necessarily, irrespective of once again finding the frequency responses then and there. It is better to remember these particular magnitude functions and can apply in a typical problem wherever it is necessary. That's it for this lecture. In this lecture we have derived the frequency responses of various kinds of impulse responses, differentiated based upon their symmetry as well as the number of samples that they have. Thank you for watching, and you can post your doubts in the comment section. Thank you.